Hi everyone, sorry because I cannot participate in person. Today I'm class to on behalf of the on authors to present our work, which is introduced about EneCross, a scenario-based simulation platform for local energy communities. And my name is Tu from Eindhoven University of Technologies in the Netherlands. So the presentation will include first the introduction, then move to the high level architecture of the platform. After that, I will show the platform interface, then move to the demonstration in a real case study, and finally with the conclusion. So first, I would like to introduce about the background. The pressure to produce CO2 emission drive the ongoing energy transition. And in this transition, buildings are evolving from the passive consumer to active prosumer with the installation of PV, battery, heat pump, and their own control strategies. This shift indeed support to the emergency of the local energy community, which is group of residential, commercial, or institutional buildings that coordinate their distributed energy resources to increase their sustainability, flexibility, and self-sufficiency. So I review existing some commercial and research tools to identify their capability and limitation for the local energy community design. And indeed, for the commercial tools like the Energy Plus, Open Studio, and Design Builder are either too complex, um, mostly focus on the single buildings or the lack flexibility for community scale modeling. Um, and on the research side, tools like DEMKIS, PyLisa, or PyPSA provide the advanced control and large-scale modeling, but they are code-based and lack user interface. So this reveals the need for the user-friendly, scenario-based platform to support building and local energy community design with KPI evaluation to guide the decision making. And indeed, with our developed platform, EneCross it can support for the detailed building simulation for the multi-building coordination with the distributed energy resources control and flexibility integration. Also support for the scenario-based planning, provide a user-friendly interface, and have the KPI visualization, and it can export the simulation result. So then now I present about the high-level architecture of the platform. So user will provide the key inputs including the historical data of the demand profiles, the PV generation, and the building parameter files, also the access parameter and the scenario configuration. Meanwhile, the external data sources like day-ahead electricity price, the CO2 factors, and the weather data are preloaded into the system. The core of the system is the EneCross engine, so which handle user requests, load the necessary input, and then coordinate the simulation process. The simulation controls is handled through the FlexMS, that is stand for Flexibility Management System, which is a flexibility engine that contains components, models, and optimization strategies. It enables simulation at both the building level and the local energy community level. The results are then passed to an interactive dashboard where the user can visualize the outcomes, compare the scenario, and export on the entire year simulation result. The KPI here will include the cell consumption, cell sufficiency, the battery use, the operational cost, the CO2 emission, and overpeak indicator. So then at the top left, so the platform will calculate the thermal electricity demand from the building parameters, weather data, and the retrofit package. So here the which is the innovation of the insulation, windows transmittance, and the infiltration rate. In the Flex MS, the control strategy includes building PV and battery models. They are implemented using the Python and the PyOmo environment. So, and they can apply at the two level. In the building level, the goal is to minimize the grid exchange, then maximize the self-consumption. And at the local energy community level, it targets to minimize total operational cost, considering the penalties of the PV curtailment and the demand flexibility. So both control strategy level are constraints to the balance power equation, capacity contract limit, and the battery constraints. In the local energy community level, the control logic work across two configurations with the community battery or the individual batteries, as you can see on the screen. So then I would like to introduce about platform interface, and this one is the home page of the platform, which navigate to the building level or the local energy community level page. And this is the building level page where the user can configure different scenario to run the simulation. And this is the local energy community level. So where the users can manage the local energy community run the simulation with the different configuration. And here is the visualization page. So where the user can analyze the result, export the simulation data, and compare the simulation side by side. So in this demonstration, the platform is applied to the BAM campus, a construction service company in the Netherlands, which includes one cluster of building ABCD and three standalone building EFG. So the simulation is set up based on the different PV size, the battery capacity, the state of charge limitation, the thermal demand, and also the local energy community battery configuration. So the simulation include both the building level and the local energy community level. Here I want to focus on the local energy community result. The rest can be shown detailed in the paper. And you can look at about the result here and see that under no peak, the scenario B6 to B9, both the community and individual battery achieve the same cell consumption and self-sufficiency, with the roof setup has lower cost. When the PV pushed to 5 times as the B10 and B11, the system hit 78 hours over peak, and thanks to the control strategy, it prevents around 4,800 kilowatt-hour peak to the grid. The individual battery then show better on cost and emission, while the community battery is better in cell consumption. And in this, so the user can generate more and more scenario to make the comparison, to make the final decision for what side of battery, what side of PV they would like to install. In the conclusion, this work addressed three core objectives. First, we developed the web-based platform for scenario configuration and comparison at both building and local energy community level. So we implemented the modular energy models and control strategies, which include the building, the PV, the battery, and the control strategies. So we already validate the platform in the real-world case study to demonstrate the impact of the design choice on the KPIs. However, there is still some limitation. So, for example, we apply the uniform control strategy for all buildings in the local energy community. We do not integrate the real-time data and the forecasting model. There is no business model for evaluation and calculate the payback periods of the assets or the flight cycle analysis. Looking ahead, so the future work may add more assets like the EV and the heat pump, implement more advanced control strategy for different buildings in the local energy community, and include the economic evaluation, implement the real-time data processing for operation phase. So if you guys have any question, just feel free to reach me through the email I already put here. And I'm the PhD candidate in Electrical Energy System Group in Eindhoven University of Technology. So thank you for your listening.